Alright, welcome everyone to Physics 2. So let me first acknowledge and celebrate the first Australians on whose traditional lands we meet, for those who are in Australia, and pay our respect to the elders past, present and emerging. This course has been developed by a team of lecturers. The voice with a French accent you are hearing at the moment comes from the one on the far right of the slide. So what is Physics 2 about? Our everyday experience tells us we live in a classical world obeying Newton's law. However, although a large fraction of the world around us can be described with classical physics, this is only a limit of more fundamental theories such as quantum physics and relativity. Together, they describe what we observe in the world from infinitely small scales of fundamental particles and interactions up to the scale of the universe. These theories are not just beautiful ideas about how the world works. They also have more and more applications benefiting our societies. For instance, relativity is used in the global positioning system as well as in fission reactors like this one in Australia. These reactors are used for various applications such as cancer detection and treatment, material imaging, and in such countries like my native one, electricity production. On the quantum side, the CSIRO says that Australia's emerging quantum technology sector could support 16,000 jobs and create over $4 billion annual revenue by 2040. Quantum physics has numerous applications in various sectors such as health, defense, mining, and space. It is also at the root of modern chemistry and drug development. If your major is in chemistry, engineering, and even biology, you may consider taking further courses in quantum physics. We will give an introduction to relativity and quantum physics. But before we do that, we will revisit classical physics in a more modern way, replacing forces and Newton's laws by new concepts and tools of what we call action physics. Action physics provides a particularly elegant way to see how classical physics emerges from the more fundamental quantum and relativistic theories. In addition to providing useful tools to derive equations of motion, we will see soon what an equation of motion is, action physics offers a natural explanation for symmetries and conservation laws, which are the foundation of modern physics, from the standard model of particle physics to energy and momentum conservation. We will give a short introduction to particle and nuclear physics. You can of course learn more about the standard model in later years if you decide to pursue in physics. Action physics also provides a framework to describe all sorts of oscillatory behaviors such as pendulums and waves. Oscillations and waves are present everywhere around us at all scales, and they are therefore a major focus of the course. This course has a lab component in which you will conduct experiments illustrating the tools and concepts introduced in lectures. So that's an outline of the course. The course is divided in two parts. The first part is focusing on action physics and the second part on oscillations and waves. In action physics, we start first with classical physics, but instead of using Newton's law, we will use first Euler Lagrange equations, and we will show that this is equivalent to Newton. We will also show that Euler Lagrange equation gives the concept of symmetries and conservation laws a meaningful relationship. We will also introduce what we call the stationary action principle, which is another way to do classical physics, and we will see how it emerged from quantum physics later. So we will only address basic introduction to quantum physics. As I said, you have further quantum courses in later years. Nevertheless, we will try to do some realistic applications, in particular looking at the spectrum of the hydrogen atom. We will then move to light and optics. Light is a specific case because, as you know, it's made of photons which move at speed of light, and whatever moves at speed of light require relativity. So that will give us a natural introduction to relativity. We'll spend a couple of weeks on relativity and its application to in the context of elementary particles and fundamental interactions. In the second part of the course, oscillations and waves, you will look at mechanical and electrical oscillators. You will see what we call speed of waves, and you will revisit the concept of light in terms of electromagnetic waves and photons before looking at applications in ray optics and see how we construct lenses, telescopes, microscopes. You will see how our ears and eyes work, for instance. And you will also study the very important concept of diffraction and interference, which has lots of applications.